Hello and welcome to the LMI webinar series. My name's Aaron and I have with me today Dan and Len. So Len Chamberlain is our Chief Commercial Officer at LMI Technologies and Dan Howe is our Regional Development Manager. Today they will be discussing the 3D scanning pyramid of greatness. Now you might be wondering what that is and I won't get into it. I'm not going to reveal anything. I'll let them divulge that. Before we get started, just a few housekeeping items. If you have any questions, please use the chat on the right-hand side. You'll probably notice that you're not able to turn your audio on and speak. So if you do have questions, please put them in the chat. We will address them when we can. We'll do our best to answer all your questions. The second part is this is being recorded. So if you have to leave or if you have someone who wants to watch this later, we'll be putting this up on our LMI YouTube channel. You'll also find this in your email box if you're watching this right now and you have to. So without further ado, I would like to hand it over to Len and Dan.
Hello, everybody. Thanks for joining. You might be wondering what the pyramid of greatness is for 3D scanning. It's modeled after Ron Swanson pyramid of greatness from Parks and Recreation. I don't know that Ron is terribly popular in Asia, so you may have to Google him to look him up, but he's a personal hero of mine. And he's got certain building blocks that essentially turn boys into men and build a great life. I thought we could do something similar with the Gocator and our scanning technology. I'm going to put my pencil down so I don't irritate anyone. We've got a number of different levels. I've got a lot of time to go through those, so I'm going to skip ahead. But the main reason that we need a pyramid of greatness is that there is a lot of choices. Even within the LMI portfolio, we've got laser sensors, we've got snapshot sensors, we've got red and blue and infrared lasers, we've got line confocal sensors. We have fields of view that span a huge array. We have single points, we have multi-dot sensors. There's a lot of different choices and a lot of different applications. And so the intent of the pyramid of greatness is to be able to narrow you down and select the right technologies for your job and help you build that complete solution. And so we're going to go through layer by layer how you make those choices and what some of the trade-offs are. So this is our pyramid. It's a little less fancy than Ron's, but we start building it up with data quality, which is you can't measure what you can't scan. And then we'll go through higher and higher level tiers. And this is also a little bit like Pavlov's needs, right? You can probably get by without some of these particular features in your sensor or in your system. But the very basic stuff like data quality and range and resolution and that sort of thing, you absolutely need. And as we get closer and closer to the top, needs get closer to wants, and it really just builds to kind of the cherry on top of the cake there. So I'm going to start it off with data quality. Data quality really is the baseline. So obviously, in my business, what I like to see is matte white parts, right? And so a primed body in white automotive application, gosh, that's perfect, right? Unfortunately, not every part looks like that. Some parts are shiny, some parts are translucent. It can also have to do with the environment that the part is in. It may be indoors, maybe outdoors, maybe underwater for that matter. How do you pick the right sensor to match that particular material? And so we're going to talk a little bit about the options that we have at LMI and how you narrow down on those options. The first thing really is the family of sensor that we're trying to select, and that has to do more with whether or not there is relative movement with the part or not. So if you see on the left side of your screen, LMI makes a full line of snapshot sensors. That's the G3000 series, Gocator 3000 series. And they can take 3D data on stationary targets. And so typically the snapshot sensors are used when there is no movement of the part or when you're at a end of arm type robotic application. Then we've got laser profilers, which do require relative movement between the part and the sensor head. And that's similar with line confocal sensors, or LCI sensors. Again, they are a line profiler just with a different base technology, and specifically geared to fairly small fields of view and quite highly specular parts. I'll talk about those in more detail here in a minute. You will find that most of this presentation focuses on the laser profilers. We have a lot more laser profilers than we have any other type of sensor. That is because they're more widely used, I think, than any other type of sensor. So we do kind of delve a little bit deeper into the laser profilers than we do the other product lines here. Data quality. So I was mentioning there are a number of different types of applications. On the left-hand side here, we've got red laser scanning a very opaque object, in this case, a potato. It's matte. It's got very low specularity. Red laser is a good choice for that type of target. We make blue laser line profilers as well. Blue tend to do better with specular surfaces and semi-translucent surfaces. They also perform slightly better than red in sunlight conditions. And then we have, for outdoor scanning primarily, and this is transportation, road scanning, rail scanning, infrared, a series of near-infrared laser sensors. And so one caveat to the last group there is that they do come with safety concerns. You can't see a near-infrared laser, so you need to take extra precaution when using them. Data quality. So one of the things that I mentioned, and I'm not sure this is going to work very well because I just noticed that the slides slide back and forth. I was really hoping they would just kind of flash. But you can see that this is a test we did on a rail application, and even though the points here are rendered in red, this was actually a blue laser application. This is a 2450 blue, and we were trying to test whether or not the sensor could still. Oh, there you go. Somebody's doing it for me. Sensor could still detect the rail surface in broad daylight and rain at the same time, and so a nice test, and the high-powered blue laser in this particular application did a very, very nice job. I'm assuming that's you, Aaron. Thank you for doing that. But in sunlight conditions, you have two choices there. You can go with the high-power blue laser, or you can go with the near-infrared lasers. I think the blue are slightly, well, actually, both have a very solid installed base in that particular setting. I mentioned I would talk a little bit about confocal technology. Confocal is another line-based profiler, but rather than a single wavelength stripe, the stripe is broken up into different wavelengths that represent different depths along the focal plane. And these sensors are really quite special. They can deal with extremely specular parts, mirror surfaces. They can also return multiple scan layers through transparent parts. So if you've got a piece of glass and you want to measure the top surface and the bottom surface, you can do both with a confocal sensor, provided that they both fit in the measurement range. They're extremely high speed and extremely high resolution. I'll get into a couple of applications for the confocal sensors a little bit later in the presentation. Actually, I'll talk about one of them right now. This particular slide shows a confocal sensor measuring the seal on a sterile medical package. This particular sterile medical package comes with a clear shell. So there's a clear blow molded plastic shell or thermoform plastic shell. And then there's a piece of Tyvek, which is heat sealed to the shell to form that sterile seal. And what the chromatic confocal sensor is able to do is to be able to pick up the top surface of the plastic, which is this top white line, the bottom surface of the plastic, which is the second line, and then the very lowest line, which blends with a second line in the middle where it's sealed, is the Tyvek paper itself. And so you actually get 3 surfaces in certain portions of the scan, and then only 2 surfaces in the portions of the scan where the heat seal has been made particularly well. I'm going to show a quick video of this, just so you get a little bit better idea. So this would be the scanning, and pretty much real time on that particular video. And this will give you a little bit of a slow motion of what the scan data looks like, as well as the intensity data that is returned by the focal spec sensor. So starting about here, you can see there's a gap between the paper and the plastic surface, which is detected as a defect by the sensor. This is something that, as far as I know, no other sensors on the planet can do, at least not do very effectively. So it's a pretty unique sensor, and this is just one of those applications. The last item to talk about when we're talking about data quality is surface. So it's nice if you have one uniform surface. If you got one shiny surface, it's a blue laser. If you've got, if you're scanning roads outside, near infrared or blue. What if you got multiple surfaces? You've got shiny or you've got dark, and you've got everything in the same package. We run into this situation quite commonly, and what typically is used inside the Gocator is a multi-exposure mode. And what multiple exposures do is interleave high exposure frames with shorter exposure frames and take the best data for that particular surface and combine it as the sensor sweeps the surface. And so here you can see the inside of a mobile phone, which has got a number of different surfaces, really white, really dark, and maybe shiny. And by using that multiple exposure mode, we can combine all of those different frames and different exposure rates into a very nice, clean surface for that data. So a lot of choices, and I think one of the things, one of the strengths of the LMI portfolio is that we do offer that broad range of choices so that you can pick the right sensor for the material you're trying to scan. Next, we'll move on and move on to resolution and range optimization. Typically, you've got a part that is so big, so you need a certain field of view, and then you've got defects which are so big, so you need a certain resolution in order to detect those defects. How do you achieve those? What are the trade-offs involved? I'm going to have to try to pick up the speed here. This diagram really shows you that for every line profiler, there's an imaging unit in the camera, a sensor in the camera, which has got a certain number of columns in the camera or in the imager itself. And each of those columns corresponds to a certain amount of real estate along the laser line, which we call X resolution. And LMI sells a number of different lines of laser profilers. So the 2100 is a VGA resolution, the 2300 1 megapixel, 2400 and 2500s go up to 2 megapixels. The difference there being the 2400 is slower speed than the 2500s. If you look at the snapshot sensors and the LCI sensors, the same sort of methodology applies. In snapshot, it applies in X and Y. And for the line confocal, you have a very, very high, typically very, very high resolution along the line. It's about 1900 points, I think, along the line for most of our confocal sensors, and a relatively small field of view. Moving along, if you plot these out in a grid, and this slide will be made available for you after the webinar. But this kind of shows you what the field of view looks like based on our different Gocator models. And so the series number 21, 23, 24, 25 designates overall resolution and speed. And then the next numbers going from 10 up to 90 really indicate small field of view up to almost 2 meter field of view in the case of the 2490. So you've got a lot of different range. Dan did a nice graph here to kind of plot it out, which shows the y-axis here is the X resolution. That's the spacing between the points you will get along the laser. I'm at the low end here where it's 6 micron resolution. So very, very tiny spacing between the points. And at the high end, we're somewhere between 0.5 millimeter and 1 millimeter between our point spacing when we're out at a 1 meter or a 2 meter field of view. And so this particular plot does a nice job of helping you narrow down on which type of model you're interested in. The one caveat to that is, let's say you need, let's say I really, really need 50 micron resolution, but I need it in 500 millimeter field of view. There is nothing in that space. And so what LMI has allowed you to do with the Gocator is called buddy mode. And buddy mode and multiple sensor layout allow you to synchronize multiple sensors along the same laser line to achieve very high resolution and larger fields of view. This is all managed within the Gocator software itself. It does the multiplexing of the lasers, so there's no interference. It automatically aligns the coordinate systems from the multiple sensors so that when you apply measurement tools, you can apply it to the entire line of data. And as you can see in this graphic, they can be arranged along a line. They can be arranged in multiple different combinations, also in a ring, in what we call reverse buddy mode. So you can eliminate some shadowing, etc. There's a lot of different configurations that are available. And alignment is more or less automatic within the Gocator software. So I went really fast, and one of the things that we did build a tool into our website, lmi3d.com. Please go. And that tool is there within that site. There's a product selector, and that really does help narrow you down on resolution that you need and the sensor model that you need from a field of view, resolution and speed standpoint. That's not, however, the pinnacle of the pyramid. And for the more difficult bits, I am going to turn it over to Dan.
All right, thank you, Len. So Len kind of went over the two base layers of the pyramid, which is really very important, which is the getting the right sensor type, whether it's a line confocal or the laser line or the snapshot, and then selecting the proper model. Once you've done that, then it's really a matter of optimizing for your specific application. And one of the things that you typically optimize for is speed, especially with line profilers. So you need to ask yourself some questions about how fast is the process. If it's an inline scanning with motion like a conveyor, how fast is that conveyor? What type of resolution do you need along that travel distance? And these are the type of questions that you'll need to ask to understand where you need to hit in terms of speed, in terms of profile rate. So we're going to focus mostly on the line profilers for this, because that's typically where the high-speed applications, that's where the line profilers are used. So some of these questions, as I mentioned, cycle time, So that's, how much cycle time do you have for the measurement? If it's a snapshot type sensor, if it's moving, how fast is that conveyor moving? And you also may want to ask yourself what kind of spacing do you have between parts? Because that'll also allow you how much time do you have to calculate when you're doing measurements. So this can get a little bit complex, but I'll try to demystify it for you a bit. And this is true for all of the line profilers, including the Gocators and the LCI sensors. They all come with a native imager speed. And so that first section there, section A, we're looking at the 2100 and 2300 series being at 200 hertz. Now that's full window profiles per second or images per second. It bumps up to 400 profiles per second at the 2400 series. And then the 2500 series is much faster at 2000. And then our LCI products are even faster at 3000. However, that is a limit if you're using the entire window. So part B there, that section B, that is a way to make things faster. And you typically do that by using less pixels on the imager. So it's what we call windowing. And so generally, this is more easily done in the Z-axis, where oftentimes you have product that has a certain width to it, but it's not particularly high. One example would be what Len had shown on the medical packaging. You have a fairly flat surface with not a lot of depth to it, and that allows you to window down and increase that speed. I should note that this is a nonlinear type effect. Usually windowing in the far field to a certain height level is faster than in the near field because there are more pixels in the near field than there are in the far field. Then there's a way to increase it even further. With the Gocator specifically, you can actually skip rows and columns. This is a way to, after you've windowed, to sacrifice, whether it's Z resolution or X resolution, to gain speed in the travel direction. There's some trade-offs involved there. And they can vary a bit from family to family, but it is a way to go even faster without sacrificing depth of field. And I will show you this in an example here just after this slide. Then we hit this section D here. This is a limit that all sensors have, whether it's even a 2D camera has this, as well as all line profilers, whether they're LMI line profilers or any other manufacturer of line profilers. You are exposing that array, and you have to expose it for a certain period of time. So you can never go faster than the exposure will allow. So even if you've windowed down and you got something running at 5 kilohertz, if you have a 1 millisecond exposure, your maximum G is going to be 1 kilohertz. And that's because it has to expose for that long. And even though your imager can handle it, the sensor won't go any faster than that exposure. Now, Len mentioned the use of multiple exposures. That is often used to get better data, and that does have a cost to it. If you use 2 exposures, that will drop your profile rate in half. So it's one of the things to also consider when you're optimizing for speed. And then finally, the final limiter is processing. So you can scan your object and get as much data as you can, and then depending on your tool set and how you're processing it, you will hit a limit as to how fast you can go. Now, all of these limiters we do have solutions for. So on the exposure limit, we do offer sensors that have higher powered lasers. So that would allow you to reduce your exposure. And then on the processing side, we do have a device called a GoMax that allows you to add processing to the system and reduce the effects of that limit, so you can maximize your speed. So I'll give you an example, and I'll show you just a real quick demo of this using our emulator. So assume you have these potatoes. Len mentioned this before and showed this image before. Let's say they're going down, singulated down a conveyor, and the potatoes have a maximum size of 100 millimeters by 100 millimeters. Let's say the user says, I want to know the size of these to a millimeter resolution. And let's assume you have a line speed of 300 feet per minute. If you calculate that out, that's about 1.5 meters per second, or 1,500 millimeters per second, which means if I want to get a slice at the very least every millimeter, I need to go at 1,500 profiles per second, or 1,500 hertz profile rate. And so how would I do that? I'm going to pull up our emulator here real quick. I'm going to share my screen. And so this is simulating a potato of roughly 100 millimeters high and wide. And you'll see I'm using a Gocator 2350 for this. And I purposely chose a 2350 because I have a very large window, yet my resolution of a Gocator 2350 is plenty to get the width and height resolution that I need. But I have a very large window, and that will allow me to window down. You'll see that my profile rate here is 181 profiles per second. That's the native resolution of this particular model. And I can actually go in here and reduce this field of view to something much smaller. Here it's about 400 millimeters high, but I only need, I'll put something slightly higher than the 100 millimeters to give myself some room. I'll bring the sides in here a little bit. And we've got something a little bit larger than a 100 millimeter window there in X and Z. And then I will save this. And you can see over here on the profile rate, it's gone up to about 2,000 profiles per second. I needed to hit 1,500. I was able to hit 2,000. And now I can run at that speed. If I wanted to go at higher speeds, I can entertain the idea of sacrificing some resolution here in the X and Z and subsampling that. And that will further increase my speed. Right now it's at about 3,000. One of the reasons it's at 3,000 is actually this exposure limiter that I mentioned. This exposure is at 300 microseconds, which means I can't go faster than 3,300 profiles per second. If this was lower, say 100, the speed will increase. Now we're at 5 kilohertz. And of course, if it was higher, let's say it was 1 millisecond or 1,000 microseconds, we're down at 1 kilohertz. So that's kind of a quick look at the speed limitations. If this was a live sensor, you'd see this CPU bar, and this would tell you if you're having processing issues and whether you'd need to add a GoMax to the system. Okay, let's see, how do I get the presentation back on? All right. I should mention with multi-exposure, here's another kind of look at it. Len showed a slide there related to the LCI. It works the same way on a Gocator. Here I have a dark object and a light object. The reason I have it here in this section of the pyramid, because it's also another way to optimize. You're optimizing for speed, and sometimes you may optimize for exposure. In this case, we used a two-part exposure, one at 100 microseconds, which is all of the red points here. So that's the lighter surfaces. And then one at 2,000 microseconds, which is this pink color, which is showing up on the black. Again, this dropped my profile rate from about 200 profiles per second down to 100 profiles per second. So that's one of the costs of doing multi-exposure. You don't always have processes that require a lot of speed. So if you don't need the speed, it's often a good idea to use multi-exposure if it doesn't affect your overall speed. A note about the snapshots, they work a lot differently. They're not line profilers. They scan an area and they use structured light. And so that process that we use is called fringe projection. So it runs through a sequence of patterns. And this requires both the sensor and the object to be stationary for a short period of time. It's usually between 100 and 200 milliseconds. But it generates all of those points in that area. So millions of points. For instance, our Gocator 3506 has 5 megapixels. It'll generate 5 million points. And so that does take time. Without acceleration, it generally takes between 3 and 5 seconds. But if you use a GoMax, that can knock it down to as low as about a half a second. But oftentimes these applications are used on robot arms where that sensor may be moving from point to point. And that's plenty of time where you can do a snapshot, maybe a second goes by, and while the robot's moving, you're calculating, and then you're ready to measure again. And again, the GoMax itself will enable an increase in speed there. So level 4 of the pyramid. So now you've got the sensor that you need, you've optimized it. The next thing is to measure, use some tools to measure your object and get the answers that you're looking for. So this is really about using the smart solutions that are available. The Gocator does have a suite of onboard tools, and really it's up to the user to customize that, but we also offer other solutions as well. And so I'll go through those. Our tool set's pretty extensive. Every new firmware comes with more and more tools. The basic tool types are, there's a whole suite of profile tools. These are looking at profiles. You can actually scan a moving web and use a profile, or you can scan objects and use section cuts to get profiles. And there's a whole bunch of tools that are related to profiles. And then we have a set of surface tools, which are just what they sound like, tools that you use on 3D surfaces. And then we also have scripting inside the sensor, which I'll show you. That's the ability to take measurements and write a little program that produces an answer that you're looking for. You might take multiple measurements and do some math inside the sensor. So these are all things that work inside the sensor. So I'll show you another example here using the emulator again. And we will grab this one. So this is a circuit board that was scanned on a linear slide using a Gocator 2520. We can look at the 3D data here, and it's a pretty nice scan. We're getting a lot of height differences. I also have our intensity on there showing that. And I created a fairly simple tool set in here. And I'll just show you what I did here as an example of some of the tools, including surface tools and a profile tool. So one tool that I made is something called Surface Edge. This is a tool that generates an edge. I use this feature box, and I'm looking to find this edge of the circuit board. And I'm going to use this later as an anchor. So what I'll be showing you is not only how to create tools, but also how to link them together. So for tool number 1, Surface Edge, so there's some open parameters here that can be adjusted. The one thing I did adjust was an outlier fraction. This allows you to say, well, if I take 90% of the points on this line, I can have 10% outliers, which are the red points. And then it fits a line to that data and creates an edge. And that will give me something like an X position, but I also can get the angle of that edge. In this case, it's pretty much up and down, so that's a 90-degree angle. The second tool I created is another Surface Edge tool. So I've labeled one Surface Edge left, and I got this one, which is called Surface Edge bottom. So same exact process, except I'm looking at the bottom here, which also gives me an angle and an X and Y position. The next tool I created is a tool called Feature Intersect. And what I did with this tool is I fed in feature 1, which is the line from the Surface Edge left, that first tool that I made, and then the line from the Surface Edge bottom, and it finds an intersect point. That's that dot here at the bottom left, and I have an XY parameter. And the reason I want to know this is that I want to know exactly where my object is, which I will use as an anchor for my main tool, which is called Surface Dimension. So this is a feature that I want to look at on my circuit board. It's basically a little button, and I want to know that that button has the right height to it there. And you'll see if I zoom in here, we can see the two feature boxes. One is the main board level, and then the button. And what I've done with that tool is I've used the intersect point as an anchor. So I have on this tool anchoring, which allows me to anchor these feature boxes so they're in the right spot to the X position and Y position of that intersect point that I made on the feature intersect tool. And from that now, I could have multiple objects going down the conveyor from various degrees of rotation and position. And this tool will find that button every time and compare the height. So I'm getting a height value, so a Z differential of this tool of 1.89 millimeters. So that's that height difference that we see. And with that tool, I can put in some open parameters and say, is it good or bad? Is it, is it between 1.8 and 2 millimeters? And that will return a green pass value. So that's one way to measure this. The other way to measure this is I can use a section cut. So what I've done is I've created a section. And so using these tools, I can anchor this section to the anchor point that I made previously, but it's actually taking a section cut across this yellow line here. So it's cutting across that button and that surface. And I'm using a profile tool here called Profile Dimension, where I fed in the section cut profile. And now I have this profile that you saw of that section cut. And I used a different tool here, a profile tool called Profile Dimension. And we're getting the same height here, 1.891 millimeters from one piece to the other. All these tools are available that can be sent out from the sensor through Ethernet or through PLC protocols. As I mentioned, we also have scripting. So if I make a bunch of tools in here, I can actually create a script. If I want to do some math in that script, it's basically a little bit of programming language which allows the user to do various calculations if the tools themselves don't give the exact answer they want. It's a way to do math between your tools and create a unique output for the sensor. Okay, so we'll go back to the presentation here. So these are what we call onboard smart tools. Now, what if you have a very, very unique need? And this is where LMI does have the capability to create special tools for high volume applications. So you may have real specific need. One example, for instance, is this track tool that's used for adhesive beads. So it's a very specialized tool. It wouldn't generally exist in the tool set, but it does now because we've created this tool. There are times where users have needs that are very, very specific, and this is where we can make what we call rule-based customized solutions. And generally, these will run on, typically you might need the GoMax to run them because the GoMax adds a lot of computing power, and often the unique special tools are oftentimes a little more complex than our typical traditional tool sets. Another way to craft solutions is to not use the typical rules-based approach, but if you've seen some of the LMI news, about a month and a half ago, we acquired Fringe AI. And so now LMI is beginning to develop and work with AI capabilities. And so this is really not using rules-based, but using the inference engines of AI, being able to do teach and train and label what's good and bad. This is often what is used for defect detection, classifying objects, segmenting objects. So things that aren't quite as defined by a concrete set of rules. So we have entered the AI field, and this is done not only with 3D, but we can also do it with 2D. And one of the things that enables that is this GoMax. So the GoMax, inside the GoMax is an NVIDIA Jetson GPU processor. This is the principal device that is used in AI these days. So it's multi-core, it has GPU acceleration. It enables a lot of things with our products, including Gocator and LCI tool sets, Sometimes we do very complex measurements with multi-sensors that involve generating very large point clouds, which this GoMax will enable. And then it also enables our future AI solutions because it runs the AI inference engine. And so now I will hand it over to Len again for the final layer of the pyramid. Len, I think you're muted.
I am muted, thank you. You always do a very nice demo, Dan. So for the cherry on top of the pyramid, we want to talk about how do we transmit the data. You know, there's a number of different requirements there. Sometimes the information needs to go to PLC. Sometimes it's going into industrial PC. Sometimes you need to capture data or build an HMI to complete your vision solution. We have help in that regard for most of those items. Relative to connecting the device to a PLC or multiple devices to a PLC, you can also connect them into the master if you're running multiple sensors. But you can see, and again, these are available in the emulator as well. We've got a number of Ethernet IP protocols, including our own Gocator protocol, Modbus, Ethernet IP. Also have a Profinet protocol as well, which is not available on the emulator. You actually need hardware to run Profinet. Besides communication to other computing devices, we do have digital outputs and analog outputs. So a digital output can be used to trigger a gate, just to, you know, if your task was sorting potatoes of a different size, that digital output can actually be used, and the Gocator can track those individual potatoes and fire the gate when it passes the exit for the right size potato. So there are applications on the simpler end where you don't even need a PLC. You can use that digital output to control your production line. That reduces the cost, obviously, simplifies the system. One of the items we added in our last software release was an addition to our SDK. And the SDK is what you would use if you were building or wanting to integrate data into your own application and building an HMI for your inspection machine or your production management system. And as you saw with Dan, the Gocator's got some really nice features in terms of 3D visualization and a dashboard that outputs its various tools and keeps statistics on the various tools. Those sorts of controls are already built within our SDK. And so although it does involve some programming, it greatly simplifies the programming that you have to do in order to be able to access the controls for a Gocator. So simple things like start, stop, execute alignment, etc., but also more sophisticated things like the 3D visualization are included in that SDK. So you have climbed the pyramid of 3D scanning greatness. You are all experts, and if you don't feel like an expert right now, there is still a way to become one, and that is to ask for help. LMI has got a large team of professionals who are much better at this than I am. And typically the way we would work is we've got laboratories set up on various continents. We scan a lot of parts in those laboratories. We have access to every sensor we make, and we can produce beautiful scan data that we can send to you along with a link to our emulator, such that you can see the 3D data yourself, manipulate the tools, build your own little measurement plan within the emulator, and experience what it's like to run the Gocator without actually investing in the hardware. So I encourage everybody to take advantage of that service if you're interested. Your distribution partner in your region can also connect you to this service, so please feel free to take advantage and let them know that you'd like to have a part scanned. One way to connect with that is via the LMI website. You can contact us at lmi3d.com. And remember to look up the Ron Swanson Pyramid of Greatness, and we will put our video right next to his, and hopefully do just as well. 45 minutes. Okay, that was a little bit longer than we wanted to go, but we are done. If there are any questions, we can answer them now.
Absolutely. I do see one couple of questions, mostly around AI. One would be, what's your scheduled roadmap? Nothing too technical today, but just what's your scheduled roadmap? When can people expect to see the AI? And I think the other one is AI applied to the 3D data?
So we have already applications in the field where AI is applied to 3D data. It has been on a case-by-case basis. So as Dan mentioned, the acquisition with the Fringe AI Group was just earlier this year. And so we are still assimilating, I guess is the right word, and building the AI solutions team within LMI. The objective of that is to migrate those Fringe AI tools into the greater Gocator software ecosystem such that they are more generically available for everybody. Those tools, as you might imagine, are sophisticated, require modeling and labeling and quite a bit of assimilation into our own code base. So we're expecting that as in terms of just general availability, it will be 2022 before you see that in kind of a generic form. We are working on case-by-case applications. So if you have a larger volume application where AI tools are necessary, then please let your LMI representative know, or Dan or myself, and we can certainly connect you with the right people and get to work.
That's great.
I just want to point out that Fringe AI does have, successful AI applications in the field using Gocator data. They're out there. As Len mentioned, it is limited right now because of the capacity and us, merging the two companies, but there are existing running applications out there right now.
That's great. And actually a follow-up question around AI is, are you required to run a GoMax or an accelerator for all the AI tools or the AI function, or will that just run on a sensor by itself, or how does that look?
So definitely we'll require one of the versions of GoMax. So Dan showed the current version of GoMax, which is the Jetson TX2. We are looking at upgrades to the GoMax here in the near future, but the NVIDIA boards that are the heart of the GoMax units are really built as AI inference engines, and so that's what we will use to process the data.
Yeah, we don't expect, I think, because of the type of processing required for AI, we don't expect them to run on a single Gocator as is. You're always going to need some form of acceleration.
Very good. Good questions.
Yeah, those are great questions. Thank you. That is all the questions I see on our chat bar so far. I think that's it. Maybe we'll just give people one more minute. So while we wait for more questions to roll in, Dan, Len, do you have any closing remarks for the evening?
No, I appreciate everybody tuning in. Have a wonderful day. And if there's any feedback later on, my email is lchamberlain@lmi3d.com. Please feel free to ask.
That's great. I do see one question. Tarek had snuck one in before we leave tonight. He brought up that sunlight can be an issue for some of the sensors. Similarly, can the laser light be an issue for certain materials?
I haven't seen that specifically, meaning, like I could imagine like a UV cure glue, if we had really high power blue light, might accidentally cure it, but I haven't actually run across that situation yet. So I haven't seen one where the laser actually did any damage.
I can think of a few instances that it may not work as well. Blue lasers tend to work better on a translucent material because they scatter more readily. And then the other one is hot glowing metal, like hot steel.
Right.
That's going to typically glow in the red spectrum, and a blue laser is going to be better for that as well.
Right. Great. Thanks for the question, Tarek. All right.
Fantastic. All right. Len, Dan, thank you so much for covering all this. That was a lot of information today. I really appreciate that.
Have a wonderful evening, everybody, or morning as it is in Asia.
And thank you, everyone, for tuning in. Keep an eye on your email box. This video will be present in a couple hours. Thank you very much for joining.
Great.